Konstantinos. Go ahead.
Great, great. Thank you very much. Good morning, everyone. It's very nice to be able to participate in this event, even remotely. I will start by sharing my screen. Just give me 1 second. Okay, so I hope you can all see the presentation and that you can all see me and hear me well enough.
Yes, we see the opening slide.
Great, great, thank you. Okay, so this presentation is about the Moses project and specifically on the automated and autonomous technologies that we are developing in the project that will enable and will contribute to shifting cargo from land-based transportation to short-sea shipping. My name is Konstantinos Louzis. I'm a PhD candidate and research engineer at the School of Naval Architecture and Marine Engineering at the National Technical University of Athens. I am working with Associate Professor Nikolaos Vendikos from the same school. And we are coordinating the Moses project. So I'll start off by saying a few quick facts about the project. So the full title is Automated Vessels and Supply Chain Optimization for Sustainable Short-Sea Shipping. It kicked off on the 1st of July in 2020. It's a 3-year project, although we are in the process of applying for an extension, so hopefully we'll get a few more months. The total budget is 8 million euros, and the consortium consists of 17 partners from different parts of Europe, including Italy, Spain, Finland, the Netherlands. So just to give a brief context about what this project is about. If we take a look at the European container supply chain and maritime transport within this supply chain, maritime transport is considered to be efficient and green. And this is mainly due to economies of scale. So as Oderic said earlier, ships are getting bigger and bigger during these last decades. And this happens for a reason, because costs are brought down due to economies of scale. So the European Union generally aims at shifting cargo from land-based transportation to more environmentally friendly modes. So Moses tries to address the challenges that have been barriers to these modal shift targets. And short-sea shipping in particular frequently loses to land-based transportation because it generally costs more to transport small amounts of cargo with these large vessels. There is also additional costs that are due to administrative burden related to maritime transport. And also the fact that the bigger ships have caused port infrastructure to be congested because of the amount of cargo that is being delivered to them, which also causes congestion on the gates of the port. So when trucks try to haul cargo out of the port, which means that when a big liner comes and then a feeder needs to take over some of the cargo, this feeder will suffer delays, which in turn increases again transportation costs. So the idea here is to increase the share of short-sea shipping in the container supply chain by creating feeder routes that reach more destination ports, and by designing vessels that carry less cargo more cost effectively. So the main objective for the Moses project is to significantly enhance the short shipping component of the European container supply chain by exactly creating sustainable feeder services from these large ports to smaller ports that have limited or no infrastructure. On this slide, you can see on the right-hand side some examples of what ports we're looking into. And these are from the Greek islands. So we're talking about nothing more than a pier. So no infrastructure for handling cargo at all. And we also have here some of the main targets that the Moses project aspires to. So how are we trying to address these challenges and achieve these goals? In the Moses project, we are developing technologies, automated and autonomous technologies, and we're also looking into the processes to some extent. And the Moses project tries to address two parts of the problem. Some of the delays that are caused on the big ports, the big liners, and the feeder service from the large port to the smaller ports. So in this context, we are developing an autonomous tugboat swarm that is collaborating with an automated mooring system for bringing down the time that it requires for a large container vessel to be docked in a large port. Then we are developing, we're designing feeder vessel concepts that are built for the purpose of transporting containers from the large port to the smaller ports. And we're talking about a LOLO concept here, so a feeder vessel with an onboard crane. And the other major part of the Moses project is the Moses matchmaking platform, which tries to optimize the cargo flows and balance the demand and both sides of the equation. In this presentation, I will focus on the autonomous tugboat technology and on the innovative feeder vessel, as we call it within the Moses project. But first of all, I would like to say a few words about the use cases we are looking into the Moses project. We have one on the Western Mediterranean in Spain, where we have Valencia and its two satellite ports, Sagunto and Gandia. The objective here is to decongest truck transport traffic in Valencia port and connect the port with the two satellite ports directly through a feeder service. Currently, hinterland traffic in this case is handled through trucks and rail. And the round trip for this route has been estimated approximately to 85 nautical miles. What we have seen from the analysis of this case is that the feeder would be competitive to existing cargo transport options if it captured 40% of the estimated demand. This would have to happen with a frequency of 3 weekly services. And the expected cost-effective capacity for the vessel is between 600 and 700 TEUs. The other case we're looking into is in the Eastern Mediterranean in Greece, where we have a route from the port of Piraeus, which is a large container terminal, to 6 ports in the Greek islands in the Aegean archipelago. The objective here is to decongest the container terminal in Piraeus and integrate these small Greek ports into the container supply chain. This is a route of about 266 nautical miles. And we have selected these 7 ports because they represent 87% of the total general cargo traffic. What is currently happening with the cargo flow from Piraeus to these islands right now is that we have Ro-Ro ferries, which transport trucks and containers on trailers to these Greek islands. The analysis from this case has shown that the feeder would be competitive if 80% of the maximum estimated demand is captured, with at least a 2 weekly service. The frequency is 2 weekly. And the expected cost-effective capacity for the vessel is estimated between 300 and 400 TEUs, although this we have also revised this figure and we have seen that a capacity of around 100 TEUs would also be cost-effective. Going on now to the autonomous tugboat technologies that we're developing. First of all, the state of the art. There have been various tests which mainly involve retrofitting existing tugboats with sensors and control hardware, and testing remote control operation, as well as autonomous navigation and collision avoidance, although not yet in towage operation, but in open sea navigation. And on this slide, we can see the most important tests that have been conducted up to this point. In the Moses project, what is the idea here? That we have a swarm of tugboats, so at least 2 tugboats, that autonomously maneuver the large vessel, bring it into the correct position, and then the tugboats automatically inform the automated mooring system that the vessel is in the correct position, and then the automated mooring system grabs the vessel and secures it in its location. In terms of autonomy level, we have designed this system to have a captain on board the tugboats, and we have the captain for monitoring purposes, as well as for fail-safe purposes. And we also have included in the equation a tugboat control station that provides monitoring for the operation, for the whole operation, and support. Within the Moses project, for the autonomous tugboat swarm, we're developing the architecture for the sensors and what the hardware on board the tugboat. We're also developing the artificial intelligence for the autonomous maneuvering part, and also requirements for the fail-safe operation. And looking into more details about this, on the left-hand side here, you can see the architecture that we have developed that consists from a detection module. So we have determined the necessary sensors that need to feed the artificial intelligence algorithm in the path planning module with the appropriate information to conduct the autonomous operation. And then we have a control module, which in the Moses project we have taken for granted. So the control is out of the scope of the research done in the Moses project. In terms of the artificial intelligence, the approach we have taken is that we're implementing a machine learning approach called reinforcement learning to train virtual agents within a virtual training environment. And you can see the result of this training on the simulation on the right-hand side of this slide. So we're training the agents based on reward functions or rewards and penalties. And as you can see here, the agents, after many iterations, of course, have learned to maneuver the large vessel in a similar way as in a real tugboat operation. In terms of the fail-safe strategy, we have conducted a study, and the approach that we see as most promising is to identify hazardous situations during the operation that result from unsafe control, and identifying and bringing the system then into a minimum risk state. From our study, this minimum risk state is mostly manual control, and this is why we have positioned Captain on board as a fail-safe strategy, among others, of course.
Konstantinos, you have to sail
Yes.
a bit faster.
Yes, yes, I will. Thank you very much, Nick. Okay, then I will quickly go through this. Trelleborg has also developed a prototype of its Automur product. Automur is an existing product, and they have adapted their product to a smaller scale and have included some additional innovative features, including communication with the autonomous tugboat Swarm. Then we have also developed the functional design for the short tugboat control station. So the connection, the information that needs to be included in the tugboat control station, how it will be used, different use cases, and so on. Then this concept will be demonstrated in Denmark in this last period of the project. So we'll take two small workboats, a barge, and we'll try to autonomously maneuver the barge to dock it with the Automur unit. Going on to the innovative feeder. Again, I have put in this slide the state of the art. So the different concepts that are currently available, let's say. And the common features here are that the operation here is envisioned as fully autonomous and unmanned. The current capacity for these concepts is roughly up to 300 TEU. And they all include zero emission operation with electric propulsion and different energy carriers, mostly batteries and hydrogen fuel cells. Going on to what we developed in Moses with respect to the innovative feeder, we have designed different concepts specifically for these use cases and for green operations. We have also looked into a preliminary hazard analysis for these concepts, and they will also be demonstrated through model testing. Just to give a brief overview what we have achieved up to this point, these are the three concepts, one for the Spanish case and two for the Greek case. So you can see the particulars of the vessels and their form in this slide. The innovations here include sustainable propulsion, and the two alternatives are hybrid methanol and batteries, and fully electric. Then we also have azimuth thrusters for enhanced maneuverability and automated cargo handling as a first step towards higher autonomy levels. With respect to the hazard analysis that we have conducted, we have identified 9 high-risk events. The most important ones relate to the positioning of the bridge in the front, which would limit the visual monitoring of the cargo space, the positioning of the onboard crane, which may impede the operation of the port cranes and result in slower cargo handling, and of course for the open-top design, which is the Greek feeder 2 concept, water accumulation in the cargo hold. In terms of the autonomous operation, we are simulating the autonomous operation from port to port, and in this slide you can see a preliminary result from that work done by Marine. So what we're doing here is combining different models that will enable the autonomous operation from port to port and integrate them through a state machine that's used for changing between mission phases. And the objective here is to demonstrate a fully autonomous round trip. Then if we go on to the robotic cargo handling system, which is developed jointly by TNO and MacGregor. MacGregor is doing the hardware side, so the sensors that will be installed on a real crane and the control module, and TNO is developing the intelligent operator support system, which enables remote supervisory control for showing, for enabling local situational awareness to the remote operator, for dynamically allocating tasks to the remote operator. So this is a one-to-many concept. One operator can monitor many different operations, and there's also risk-based criteria involved in this dynamic task allocation. So some key takeaways from the research that we have done up to this point. And Nick, I'm concluding very, very shortly. First of all, with respect to the feeder, the competitiveness of the feeder depends on the container transport demand that is captured by the feeder. And in terms of its green operation, the hybrid power solution seems to be the most promising in terms of cost, because it is estimated to have about 10% lower operating costs compared to the battery electric option. If we look at the autonomous tugboat part, then the approach we have taken for reinforcement learning seems to be producing tugboat movements that are similar to manually operated tugboats. What is also important for the autonomous operation is knowing the tugboat position very accurately, and of course the communication with the automated mooring system, as well as with the short tugboat control station. And that it seems that human in the loop will be the way forward for safety critical operations, such as maneuvering and docking a large container ship on a large terminal. Concluding with how Moses addresses the NIADA's impact map, although the Moses scope is shortest shipping, but the targets are mostly the same. So for shifting freight to water, we have the innovative feeder that is designed to be competitive to the Ro-Ro chain and independent from small port infrastructure. And we also have the matchmaking platform, which optimizes the short shipping alternative for stakeholders. Then we have the pathway to zero emission fleet, because the innovative feeder is designed for zero emission operation. And we have also looked into the required infrastructure for recharging fully electric tugboats, because the tugboat form is envisioned in the Moses project as fully electric. Then in terms of more attractive jobs, we have looked into enabling safe and cost-effective remote crane operations. So how the remote operator will work through the intelligent operator support system. And finally, in terms of smart waterways, although we don't address this impact point directly, we will contribute by enabling the autonomous port-to-port operation of the innovative feeder, as well as through the fully automated tugboat operation. So I hope I haven't abused too much of the time. So thank you very much for your attention, and happy to answer any question. Thank you very much.
Thanks, Konstantinos. I know when boys and their toys, they start talking, those boys, it's hard to keep them under control, but I'll do my best. Any questions from online? Come on, what's happening there? Yesterday was full of people in the cloud who wanted to ask questions, so you have to. Everything is clear. Okay. Anybody here from the room who wants to talk? Question?
I'm a little bit surprised about your conclusion that there must be a human in the loop when there is a risky operation. But that's the whole situation is risky. And although you come to that conclusion, you also come to the conclusion that the next generation is fully automated tugboats. So that gives me a mixed feeling.
Okay, thank you very much for the question. Okay, indeed, this seems to be a bit contradictory. I would say that because this system is designed on a preliminary stage, and these are just the first steps, that the human in the loop seems to make sense to address, any type of failure. And I'm saying this because more research would have to be done beyond the Moses project to make a potentially unmanned autonomous tugboat swarm more fault tolerant and more resilient and all of that. But all of this requires a lot more research. So for the time being, we say that the human in the loop, the human should remain in the loop and on board the tugboat. I don't know if I
But
have.
that's based on
yeah.
a feeling and not on a proof. You didn't prove that in practice.
No, this has not been proven. This is based on a study we have conducted, so a kind of preliminary hazard analysis, and we checked the different alternatives for achieving a minimum risk state. And the result of the analysis was that most failures would be better addressed by the captain on board assuming manual control. But again, this is a preliminary study and a preliminary result.
Okay, thanks, Konstantinos. Anybody else here from the audience?
Thanks, Konstantinos, for the presentation. So you mentioned that.
Tell him who you are.
Yeah, he knows me already.
Oh, okay.
Peter. So you mentioned that for the feeder badge, it's only cost effective if they can capture at least 40% in the market demand, right? But then the question is, did you research into how these markets can be captured or these cargo flows can be captured in your research?
Thank you very much for the question, Peter. Okay, the analysis that this result is based on didn't look into how the demand would be captured. The criterion there was purely in terms of cost. So we compared the cost of the new route to the current alternatives, and the objective there was to see how much cargo should the feeder carry in order to be competitive with the current situation. And for example, 40% may not seem like too ambitious, but this is for the Spanish case. For the Greek case, 80% is much more ambitious. But we haven't looked into the ways that this demand could be captured, because it depends on a lot of different parameters, I suppose. So, for example, in the Greek case, the current state is, as I said earlier, a row of ferries with trucks on board. And this is a pretty established situation. So it would require, stakeholder engagement. And I think we will be trying to pitch the idea to some stakeholders here in Greece. But first of all, it would take some convincing, I guess. But to answer the question, no, we haven't looked into structured ways of capturing the demand.
Anybody else? Well, Konstantinos, I like those business models you have been addressing, or those cargo flows. It would be worthwhile to go much more in detail, but I guess you have to come to Brussels. I have some nice Greek drinks in my office, provided by a good Greek friend. And just like the Greek drinks, this presentation of you tastes for more. So most welcome in Brussels.